Good morning, students. Today in this session, let us discuss the week 4 program of Artificial Intelligence Lab, that is multi-layer feed-forward neural networks with both forward propagation and the backward propagation. So for this particular program, I have used this iris dataset. Maybe you are familiar with this iris dataset. It is going to have 4 features and the 3 labels. So it is a used for multi-class classification. Why? Because it is having 3 target labels. That's why we call it as a multi. It can be iris dataset can be used for the multi-class classification. So here, let us start the program. So with the very first, let us import the packages of from sklearn, where we are going to import this train test split cross validation score. And from sklearn.metrics, we are going to import the accuracy and the classification report. And the dataset already told you that we are using this iris dataset. So from directly from sklearn.datasets, I'm importing load underscore iris. So it is going to import the dataset. And then from sklearn.neural network, that is neural underscore network. Now, as we are implementing this multi-layer feed forward neural network, so just I'm implementing this MLP classifier. And then I'm importing this numpy, and just simply to ignore the warnings, just we are importing this warning. And then next, just to suppress the warnings for the cleaner output, just I have written a piece of code called as warnings.filter warnings. Just we are simply ignoring. Then the next step comes about the loading the data set. So and that I'm loading it into, I'm saving it into one object called as data. So data equal to load underscore iris, which is this where we have written this load underscore iris. And two in labels like x and y, where in x we are going to have the input features. That is, we are going to store the independent variables of that particular data set, that we call it as we are uh, giving the name as data. And then this y is the target labels, so that we are storing in the y variable. So we know that for any data set that there will be a independent variables and there will be a dependent variable. So independent variable I'm storing here, and dependent variable I'm storing here. Okay, just simply run this piece of code. So it's executed. We have uploaded the iris dataset. Now, next, it comes splitting the data into training and the testing. So here, the arguments in train and test split is, we have 4 arguments, that is X train, X test, Y train, and the Y test. So this X train is training the set features, that is 70% of independent variables we are training, and 30% of independent variables we are testing. And Y training is training the labeled, there is target label, 70% of the target labels we are training, and 30% of the target labels we are testing. So it is going to take it into 4 arguments. And here you can see that train test split X and Y, where we have given here X and Y, that is independent and dependent variables. And 30% of the whole data set we are giving for the test, and random state equal to 42. That is, randomly it is going to choose the data for training. Then the next step, here we are defining the multi-layer feed-forward neural network classifier, where we have created an object MLP underscore CLF, that, and we are calling the multi-layer feed-forward network, that is MLP classifier. And here, hidden layer, we have taken it as 100. So that is, so the number of hidden layers, 100 means there is 100 means here there is one hidden layer with 100 neurons, and this is maximum iteration equal to 300. It is going to set the random, it sets the maximum number of iterations, that is equal to 300, and again we have taken the random state equal to 42. It's nothing but it is going to set the random seed for reproducibility for the results. Then next step comes the training the classifier. For that, we are going to fit the data, that is MLP underscore CLF, this one where we have created an object of MLP classifier dot fit. So here the fit method trains the MLP classifier on the training data. Okay, for that we use this, and we are going to use the X train and the Y train. X train, that is the independent features, and the dependent features. So X train and Y train. Just it is going to print the training multi-layer feed forward neural network. That is what the output we got it. Then next one here, accessing weights and biases after training. We know that for a particular neural network, these weights and biases are very important. So here for accessing the trained weights, we are going to use a method called as MLP underscore CLF. That is what the object we have created. And it is coefficients underscore zero. That is what it indicates underscore zero is, it is weights of the first layer. That is connecting the input layer to the first hidden layer. And if you give suppose MLP underscore CLF dot coefficients underscore 1, that will be weights of the second layer connecting the first hidden layer to the next hidden layer, and so on. It will be run in that way. Similarly, accessing the biases. So created a variable biases, and we use this intercepts underscore zero. The same over here. Intercepts underscore zero, biases of the first layer. If it is intercepts underscore one, biases of the second layer, and so on. Next, the very important function in neural networks is how we are going to write a function to illustrate the forward propagation. So for that, just simply we have created a function called as def, and here's forward propagation of sample, weights, and biases. That is the input, weights, and biases. So first, here we are calling it as printing the forward propagation steps. Here, this NP dot performs the matrix multiplication. That is sample comma weights plus biases. That is the equation will be something like this. We know that this is the formula for calculating the forward propagation. For that, the simple piece of code is this one, and that we are going to store it in a variable called as Z. And here we are printing the linear output of the first 5 samples. I want to display only the first 5 samples. That's why I have written this piece of code. Similarly, after that, I am applying an activation function. That here we are using that activation function as ReLU activation function. So for that, the formula is something like this: NP dot maximum of 0 comma Z. And then here, and at last we are going to return Z comma A. That is the linear outputs and the activated outputs. So these are the linear outputs and these are the activated outputs. It is going to return. Then next comes under the backward propagation. So here the backward propagation, uh, here we are going to the main function. Here is we are going to you calculate the gradient of the loss with respect to the Z. That is the linear input. So for that, we are going to find out the dou loss by dou A. That is gradient of the loss with respect to Z. That is simply we can write it as 1 by M sigma I equal to 1 AI minus Y whole square. So that particular formula, we are going with that particular formula, we are going to calculate the gradient of the loss with respect to Z. Then we are going to calculate the gradient of weights and biases. For that, we are going to use this NP dot, which is that's what here. Here you can see it is 1 by M, the formula. That is gradient of the loss with respect to weights, that is DW, and gradient of the loss with respect to bias. Both we are going to find out. That is how we calculate the gradients of weights and the bias. And once we calculate the loss with respect to weights and biases, then we have to update the weights and biases. Okay, for that simply we write a formula, that is weights equal to weights minus learning rate into DW, biases equal to biases minus learning rate into DW, what we calculated over here. And then we are going to print the updated weights and the biases, and at last it is going to return the weights and biases. So this is simple. This piece of code indicates how we will do the forward propagation and how we are going to do the backward propagation. The backward propagation is nothing but the calculating the gradients with respect to gradient of the loss with respect to Z, and then we are going to update the weights and the biases. Then next comes, once after finishing this, the next thing is we are going to predict the output. So for that, we have created an object y underscore predict and MLP underscore CLF. We know that this is the object of the MLP classifier, and we are predicting the test data. And then we are going to calculate the accuracy score, that is y test and the y predicted, and just printing the accuracy of the given thing. And then next one, cross validation. So what is this? Why we have to perform this cross validation? So it is nothing but a cross validation is nothing but, see, let us calculate here. So we got accuracy as 1, that means overfitting. The data is overfitting. We should not get 100% accuracy. We know that. Next, for that reason, we are going to perform the cross validation. So what is this cross validation? Cross validation is nothing but it is a technique to evaluate the model's performance by dividing the data set into multiple subsets, that is different folds. So see here. So actually the model is trained on k minus 1 folds and it tested on the remaining folds, that is repeated k times. That is, we can also call it as the k fold cross validation. Okay? So for that we have written this simple piece of code. This is CV. So here you can see here MLP, the object of the multi-class multi-layer perceptron class, and X we know independent variables, Y and cross validation 5. So it indicates that 5-fold cross validation we are doing. Okay, 5-fold here. Then so this output that CV underscore scores, it's array containing the accuracy scores for each fold it is going to give us. Then next one is here we are going to next just simple forward propagation with a sample from the tested. Now here we want the output of the propagation, what we have done the forward propagation, that output I want to print over here. So you can see here just as a sample of 5, means first 5 variables, the output will be something like this. You can see here. So it is so simple forward propagation of input, weights and the biases. So see here is the first 5 samples. Okay, then here I am printing the backward propagation. That is, once we have updated the weights, what is the values of this weights and biases and what will be the output. You can see here for the first 5 samples, this is the output. And then we are going to print the classification report. You can see here the accuracy of classification report of test data and the predicted data. Still we are getting precision, recall and F1 score as 1, where we are overfitting the data. Okay. So as this is a simple data set, maybe it overfit the data, but in general, we should not get that accuracy or precision or recall as the 1. So this is what the simple implementation of multi-layer perceptron or multi-layer feed-forward neural networks with simple forward propagation and a backward propagation, where we are going to calculate the gradients with respect to the weights and biases. This is what all about the multi-layer feed-forward neural network back propagation. Thank you.